Hello guys, welcome back to another video on my channel. So far we've been doing this linear algebra lecture series and we finished our discussion of vector spaces and their properties. So I thought this is a good place to actually take a break and do what we usually do and what is so popular on this channel. So let's get started. We are going to evaluate the integral I from 0 to infinity jn of x over x dx, where jn is a solution to the Bessel differential equation for n greater than or equal to 0, which is given by x squared second derivative of y with respect to x plus x first derivative of y with respect to x plus x squared minus n squared y equals 0. This equation shows up in problems where you use spherical or cylindrical coordinate systems. You'll get this equation for the radial equation in such systems. And the solutions to this equation, Jn of x, is called the Bessel function. More formally, Bessel function of the first kind. Here we're just going to call them Bessel functions. And note that even though you can define them for n greater than or equal to 0, we're going to only use n greater than 0 for the purposes of this video. So to solve this, it is quite non-elementary. Set x to be square root t such that dx becomes 1 over 2 square root t dt. So we replace the entire thing. The limits won't be changed under such a change of variables. Jn of square root t over square root t times 1 over 2 square root t dt from the differential. So we get 1/2 integral 0 to infinity jn square root t over t dt. Now, for convenience in the later part of the video, let me multiply and divide by t to the n over 2 power. So I do that. I get 1/2 integral 0 to infinity t to the n over 2 minus 1 because we had a t in the denominator. Jn of square root t over t to the n over 2 dt. You can check that when you divide this factor up front by the denominator, you actually end up with a t in the denominator. So we haven't really violated the equality in any way. Reasons for doing this will actually become clear later. Now, we can use the series expansion for the Bessel function. You can derive this series expansion by using a Frobenius method and Ansatz series solution to this differential equation and look for termination conditions and indicial and recurring equations to actually figure out the form. But this is the series expansion. Sum from k equals 0 to infinity minus 1 to the k over k factorial gamma of k plus n plus 1. And since it's a power series, it should have a z dependence. Z over 2, the whole thing raised to n plus 2k power. So what we had before, let's call that f of t, which is just the term in the bracket. Jn of square root t over t to the n over 2. So we can pull the n over 2 outside, 1 over t to the n over 2, use the series expansion for the Bessel function. So we get sum from 0 to infinity minus 1 to the k over k factorial gamma k plus n plus 1 square root t over 2 quantity to the n plus 2k power. We can simplify things like using this factor that's outside the sum to cancel out, simplify a few things, because when you have square root t, that becomes t to the 1/2 power. So you have n over 2 plus 2k over 2, which is k. So you have n over 2 plus k. The n over 2 will cancel with that n over 2. So we're just left with k. So we have a t to the k over, in the denominator term of this factor, you have nothing special. So you have just 2 to the n plus 2k. Everything else is the same. I'm not going to bother repeating that. Now, This form is actually quite useful, and which actually justifies why we've used this square root substitution at the beginning, is to arrive at this form. And this form is instrumental because now we can use Ramanujan's master theorem. And if you recall what that is, and I've made a video on it, although the conditions in that video are stricter, and I said by the end we can expand or make the conditions weaker, so that a function that satisfies the criteria, the assumption stated, will indeed satisfy the theorem. That if f of t has expansion of the form f of t equals sum from k equals 0 to infinity phi of k over k factorial times minus 1 to the k, then integral 0 to infinity t to the s minus 1 f of t dt, which is the Mellin transform of f, equals the gamma of s times phi of minus s. So in our case, you can compare. We used the suggestive notation f of t before, because you look at f of t and you look at the the terms that match this form, you immediately realize that phi of k is just 1 over gamma of k plus n plus 1, along with that factor of 2. So 2 to the n plus there should be a 2k there. And therefore, our integral that we had, which was indeed, if you go back, it was 1/2 integral 0 to infinity t to the n over 2 minus 1 times f of t dt. It actually fits what we have for the master theorem. So we just have that extra factor of 1/2, and instead of s we have n over 2. So we're fixing the value of s equals n over 2 in our master theorem equation. So that means if we plug in s equals n over 2, we can get the right hand side. So phi of minus n over 2, if you go back to what phi is, we get 1 over gamma of minus n over 2 plus n plus 1 times 1 over 2 to the n plus 2 times negative n over 2. You simplify that, you get gamma of n over 2 plus 1 here, and the 2 will actually cancel out. You get 2 to the power 0, which is 1. So we have in the end 1 over gamma of n over 2 plus 1. Our integral was 1/2 integral 0 to infinity t to the n over 2 minus 1 f of t dt. So that's 1/2 gamma of s, and s was n over 2, times phi of negative s, which is negative n over 2. And that gives 1/2 gamma of n over 2 times 1 over gamma of n over 2 plus 1, because we calculated what phi of negative n over 2 is. Now we just use simply the recurrence relation of the gamma function. Gamma of z plus 1 is z times gamma of z. So we get I is 1/2 gamma of n over 2 times 1 over n over 2 times gamma of n over 2, because we split the n over 2 plus 1 as n over 2 times gamma of n over 2. The gammas will cancel, and so will the factors of 2, and we're just left with the simple fraction 1 over n. The simple way, very nice way of doing it. And since we have proved Ramanujan's master theorem, I thought, well, why not use it? I did make an applications video, but this definitely stands out. Also, if we play around with the original problem a little bit, we have integral from 0 to infinity jn of x over x dx. You can write the x as an exponential of e to the minus xt dt. And of course, using Fubini theorem or even dominated convergence, whichever floats your boat, you can justify interchanging the integral from t inside to t outside, like I've written here. That's a piece of analysis I'm not going to bother with. You have integral 0 to infinity, the Laplace transform, because e to the minus xt jn of x is just the Laplace transform of t, because you integrate over the x, that's Laplace transform, and that is a function in the end, output of t, which is itself being integrated. So we have the integral from 0 to infinity of the Laplace transform of the Bessel function. But all of this was still equal to I. So even the integral of the Laplace transform like this must be equal to I, which is 1 over n, because we evaluated that before, for n greater than 0, as we assumed at the beginning of the problem. That is, so we solved yet another problem. If you see Laplace transform of the Bessel function from 0 to infinity integrated, then you know the answer is just 1 over n. Also, if you take the Laplace transform, for curiosity, of J0 when n equals 0, because that's the case we basically avoid throughout the previous problem, that is by definition integral 0 to infinity e to the minus xt J0 of x dx. Use the series expansion for the J0. And again, we can justify interchanging the sum and integral by either dominated convergence or Fubini theorem. So I'm not going to do that, but we can. It's integral and the sum is finite, well defined, so we can do that. Sum from k equals 0 to infinity minus 1 to the k over k factorial gamma of k plus 1. We've just used the fact that in this case n, which was the index of the Bessel function, is 0 in the series expansion. 1 over 2 to the 2k. Integral 0 to infinity, because we had that from the beginning, e to the minus xt x to the 2k dx. The integration is very simple. So we have sum from 0 to infinity minus 1 to the k over k factorial gamma of k plus 1 times 1 over 2 to the 2k is 4k. And the integral, which is the Laplace transform of x to the 2k, you can either do this by parts slowly, or you can look this in a table if you want to avoid. If you just trust the tables, you trust your process, you know you'll get 2k factorial over t to the k plus 1. Now you can pull a 2 out from each of the terms in the factorial. So that gives us k terms. So 2 to the k times k factorial is equal to 2 times k the whole factorial. And that cancels with the 4k, one of the, so there's two 2k's in the 4k. It will cancel with one of those factors in the denominator. And we can just take a 1 over t outside from the t to the k plus 1. So we have 1 over t sum from 0 to infinity minus 1 to the k over the k factorials also cancel. So 2 to the k. But the k factorials do cancel, but we have gamma of k plus 1, which is k factorial again. So you have 2 to the k factorial times 1 over t to the k from the denominator, one of the factors. We took out the t, so the others are still inside the sum. We can write the sum individually, right? Each term of this infinite sum. So you have 1 over t outside, 1 minus 1 over 2t squared plus 1 times 3 over 2 times 4, 1 over t squared the whole squared minus dot dot dot, because it's alternating. But to those of you who are well versed in your Taylor series or your power series in general, will notice that this is actually the Taylor series for 1 plus 1 over t squared to the minus 1/2 power. So that actually becomes, with the 1 over t, 1 over square root 1 plus t squared. So that's fine. So we've solved for the Laplace transform of the J0, the 0th order Bessel function, and we've gotten 1 over 1 plus t squared in a square root. So now if we take the limit as t goes to 0, so the limit t as t goes to 0 of Laplace of J0 of t equals integral 0 to infinity. When you take the limit, and again, because of dominated convergence, you can take the limit inside, you get exponential e to the minus xt. In the limit as t goes to 0, the exponential becomes e to the 0, which is 1. So there's no other prefactor in the integrand. So you just have integral 0 to infinity j0 of x dx. We know what the Laplace transform of j0 is, though. It's 1 over 1 plus t squared in under root. But we also took the limit on both sides. So we have limit as t goes to 0 of that expression. And that's very easy to evaluate. You can simply plug t equals 0. So that gives us 1. So this is a very nice integral we've solved yet again, that the integral of the Bessel function from 0 to infinity j0 of x is actually 1. So it does not blow up. It's actually bounded, well defined, it's convergent on the entire real line, which actually intuitively also makes sense because the Bessel functions actually incorporate the radial behavior of any, say, wave or a partial differential equation, which is quite usually a wave equation that you solve. And for a wave that is spread out over the entire real plane, you want the j0 to not grow exponentially, because that would mean there are no boundary conditions. It's the wave is growing indefinitely. So since this captures the radial behavior, so as the wave goes out, the average is well defined and it equals 1. So that's a hand wavy, almost intuitive explanation for why this is 1, but this is the math to actually justify it. I hope you like this video. I know this was a little rushed, but this actually is quite a non-trivial problem, and it is exciting for the same reason. So please like and subscribe to my channel, spread the word, and peace out. See you next time.